There's a version of the future where humanity never leaves Earth again. Not because we run out of rockets, not because of politics or money. Because we fill the sky with shrapnel moving 20 times faster than a bullet, and once it starts colliding with itself, nothing can clean it up. Not in our lifetime, not in our grandchildren's. This isn't science fiction. It has a name, a real mathematical model behind it. And depending who you ask, it may have already started. It's called Kessler Syndrome, named after the NASA scientist who first modeled it in 1978. The idea, stripped to its core, low Earth orbit is getting crowded enough that a single collision between two satellites, or even a stray piece of debris, could set off a chain reaction. That collision creates thousands of new debris fragments. Those fragments hit other things. Those collisions create more debris. Eventually, you have a self-sustaining cloud of shrapnel circling the planet at roughly 17,000 miles per hour, dense enough that launching anything through it becomes a game of Russian roulette. That's the whole video. Everything after this is explaining exactly how close we actually are, and why the people who track this stuff professionally are more worried today than they were 10 years ago. Here's the number that makes this different from an ordinary traffic accident. Orbital velocity. A piece of debris the size of a paint fleck at orbital speed hits a spacecraft with roughly the same energy as a bowling ball thrown at highway speed. A fragment the size of a marble can disable a satellite outright. A collision between two intact satellites, which has actually happened. In 2009, when a defunct Russian satellite hit an active Iridium communications satellite, doesn't just destroy two objects. It creates an estimated 2,000 plus trackable fragments, and many thousands more too small to track, but still lethal. And every one of those fragments is now its own object, on its own orbit, capable of causing the exact same kind of collision again. This is why Kessler's original 1978 paper wasn't really about a single accident. It was about a threshold, a debris density in low Earth orbit, past which collisions generate debris faster than atmospheric drag and cleanup can remove it. Past that threshold, the math stops being optional. The cascade sustains itself. So, have we crossed that threshold? The honest answer is that some regions of orbit are far closer than others. Certain crowded bands, particularly around 800 to 1,000 kilometers altitude, popular for Earth observation satellites, already show collision rates that some orbital debris researchers describe as functionally cascading in slow motion. Nobody agrees on an exact tipping point, because the models depend on assumptions about future launch rates, debris removal efforts, and how good our tracking actually is for objects too small to see. And launch rates are the part that's changed the most. In the 2010s, a few hundred satellites went up a year. Now, with mega-constellations like Starlink adding thousands of satellites to low Earth orbit, that number has exploded. Tens of thousands of new objects are either in orbit or planned within this decade. Every one of them is a new node that can fail, get hit, or eventually become debris itself. More objects in orbit doesn't just mean more risk in a simple, additive way. Because of how collision probability scales, it means risk grows non-linearly closer to how compound interest works than simple addition. So play it forward. What does a successful Kessler cascade actually look like, if it happens? Not an explosion. Not a single dramatic event. Slow attrition. GPS becomes unreliable. Weather satellites go dark. Communication satellites that connect remote parts of the world stop functioning, and there's no way to safely replace them because the orbit they used to occupy is now full of debris. Insurance for satellite launches becomes prohibitively expensive, then unavailable. Space agencies start describing entire altitude bands as no-go zones, not because of any single object, but because the debris field is too dense to fly through safely. And the truly unsettling part, even if humanity stopped launching anything new tomorrow, a cascade that's already crossed the threshold doesn't reverse. It can take decades to centuries for enough debris to naturally decay out of orbit via atmospheric drag, depending on altitude. We could permanently lose access to entire regions of space for longer than any single human lifetime as a direct consequence of decisions made in a single decade. Now, the honest caveat, because it's important not to overstate this, Kessler Syndrome is not an inevitability, and plenty of orbital debris scientists actively push back on the most alarmist framings. Debris removal technology is real, and improving missions using nets, harpoons, and robotic arms to deorbit dead satellites are already being tested. International tracking has gotten dramatically better. We can now catalog objects as small as a few centimeters. And newer satellites are increasingly required to have end-of-life deorbit plans so they don't linger as future collision risks. The more accurate way to frame this isn't "doom is coming." It's that we're in a genuine live race between the rate we're adding risk to orbit and the rate we're developing the tools to remove it. Nobody knows for certain which side is winning. That uncertainty, not a guaranteed apocalypse, is the actually unsettling part. We're running a real-time experiment on a shared resource, without a clear read on the results, until it's potentially too late to reverse them. The sky above you right now has thousands of satellites in it, several 100,000 tracked pieces of debris, and depending who you ask, a countdown that may already be running. Not because of a single catastrophe, because of the same kind of quiet, compounding mechanism that shows up everywhere once you know to look for it. If that's the kind of thing you're into, the hidden systems running underneath, stuff we take for granted, that's the whole channel. Subscribe, and I'll see you in the next one.